The next thing we're going to talk about is what we generally observe from space, right? So almost all of the information that we get about stars, about galaxies, it comes in the form of light. It comes in the form of light, right? We can measure other things, we can measure neutrinos, we can measure gravitational radiation, we can measure particles that come from the space, but the vast majority of the information comes in the form of light. So we need to learn about light and how it works. Okay? So why do we use light? Basically, stars do a great job of making light. Look at the sun, right? It makes light. It's a 4 times 10 to the 26 watt light bulb. And so the light from stars is where the bulk of their energy goes, right? As they're doing whatever they do inside, they're doing something, but basically what stars do is make light. Now, stars also emit particles. Like our sun, there's this thing called the solar wind coming off the sun, which is a tiny fraction of the energy budget of the sun. We could look at the particles, but the particles, often they have an electric charge. So as they go through the galaxy or even in the solar system, they're bent. Their paths are bent by the magnetic field in the galaxy. So when I see a particle coming from over there, it didn't necessarily come from an object over there. It could have come from an object over there. So it's very hard to figure out where it's coming from. On the other hand, light, it's common and it travels nearly the same path. We'll talk about things like gravitational lensing and light can be bent, but that's really, really a tiny effect. When I see a star, some light coming from that part of the sky, I know that the object that it came from is also in that part of the sky. That's very useful. So that I can identify where the information is coming from with an object. Okay? Now, I talk about different colors. They travel the same path. What does color mean? So color is really the color that we perceive when we look at something is telling us how much radiation, how much light do we get at different wavelengths. So we can divide the wavelengths into things of longer wavelengths and shorter wavelengths. If I see something as red, that means I'm getting more long wavelength light from that object versus the shorter one. If I see something blue, I get more short wavelength versus long wavelength. Is that all making sense so far? And so the range of wavelengths that we can sense with our eye is really, really narrow. It's about a factor of 2 in wavelength. So if you think about sound, what you perceive with your ear, 1 octave is a factor of 2 in wavelength. Whereas what we can perceive, maybe we can perceive something like 5, 6 octaves of sound between the lowest sounds you can perceive, maybe around 20 hertz, going all the way up to 10,000. Maybe it's closer to 8 or 9 octaves. In light, what we see with our eye is a very, very narrow range. Okay? So that's important to realize. So there are other types of light that we cannot perceive. There is light that is bluer than blue light, and we call that, or it's more violet than violet light, and we call that ultraviolet light. And there's light that's redder than red light, and we call that infrared light. But we can go beyond that. So when we do spectroscopy, what we do is we take the light that's coming in and we divide it into lots of bins, where each bin corresponds to a narrow range of wavelength. Your eye basically divides light into 3 bins or 4 bins, which you may not realize that. But because the color receptors are carried on the X chromosome, and women have 2 X chromosomes, they can get 1 extra green, believe it or not, relative to men. So like, you might have 2 types of green receptors in your eye. So you might look at a color and it looks completely different. You could have 2 greens that to me look completely identical, but to you look different. Because you are 2 colors. Believe it or not. That maybe you've not known that, but that's kind of cool. Right, but in astronomy we can divide it into millions of bins, which gives us lots more information. And what we can figure out from that information is a lot, and we'll go through how we figure that out in a little bit. We can figure out the temperature of an object, right? We can take the star's temperature. We can measure how fast it's moving relative to us. We can infer whether it has a magnetic field and how strong that magnetic field is. Those are things we can measure almost directly from the spectrum. If we model the spectrum, we can figure out how old the star is. We can figure out what materials make up that star and in what proportions. We can figure out the mass of the star, and we can also figure out how bright it is inherently. We can figure out these numbers. Right? Now, one thing to keep in mind, if a star is far away, I have 2 stars that are inherently equally bright, and one's further away than the other, the one that's further will appear fainter. But with the spectra, we can read what is the real power of the star, and then figure out maybe how far away it is, use it backwards. So how does this work, right? So let's think about how we figure out what materials the star is made of. So let's imagine that we have a buffet of light, all different types of light, but here we have, you imagine it as different types of food, so different colors of light. Some colors of light would be grapes, and others would be steak. And we let different creatures attack the smorgasbord. So we let the lion attack the smorgasbord, and we would find that the peppers and the grapes would be untouched. But the steak would be gone. And if we let the bunny attack the smorgasbord, the steak would be untouched, and the peppers and carrots and whatnot would be gone. So the metaphor here is the lion and the rabbit are the material that the light is passing through. And depending on what atoms it is, they have appetites for different colors of light. And you'll do, I don't think you will, never mind. And what we can do is different materials will interact with light of different colors. And I'll give you some examples. But here this is showing, this is maybe the first time we've shown this. This is a logarithmic plot, right? So a given distance in the vertical direction isn't a given change in wavelength. It's a factor of 10 in wavelength. So getting a hold of it, getting a handle of how this works is going to be important in the course because things vary by a huge amount in astronomy. So we like to compress things in. So here we can see the visible light spectrum is right in the middle, more or less, here. And it's a relatively narrow range of wavelengths, from 400 to 700 nanometers. Now, what is a nanometer? A nanometer is a billionth of a meter. So what you perceive with your eye is just under 1/1,000,000th of a meter. So 1,000th of a millimeter. That's the light that you perceive with your eye. Now, if we go to longer wavelengths, that's going down the page, we see infrared radiation, which we sense as heat on our skin, for example. And when we get up to around a wavelength of a millimeter, we call it microwaves. So your microwave oven, the wavelength in there is about 10 centimeters. And you can measure it if you want to. And I can explain to you how you measure it. If you want to do that at home, you can measure the wavelength of the microwave oven. And as you go to even longer wavelengths, you get into radio waves, so going down. And these are just names, right? But it's important that we have the names. Now, if we go up, just a little bit bluer than blue light is ultraviolet radiation, and then X-rays, and then gamma rays, right? Now, when we're on the surface of the Earth, if you had this handout, you would see that on the surface of the Earth, visible light reaches the surface of the Earth, a little bit of ultraviolet light. That's no coincidence. Our eyes are evolved to detect the radiation that reaches the surface of the Earth. Right? That's why visible light reaches the surface of the Earth. If we had eyes that were sensitive to X-rays, that wouldn't be so useful. It would just be like this all the time. Right? We wouldn't see like that. That's like with Superman having X-ray vision. It's completely useless because there are no X-rays floating around here. If he wanted to see through you, he would say, wait a second, I want to see what's in your wallet. And he would have to produce a source of X-rays behind you. Then he could look at you and go, oh, but Superman never does that. He just looks, but that's BS. It's just BS, right? So X-ray vision would be completely useless on the surface of the Earth because X-rays don't reach the surface of the Earth. Now, if we go to the longer wavelengths, infrared radiation, some of it reaches the surface of the Earth in narrow bands, but generally when we go down, infrared radiation, microwave radiation doesn't really reach the surface of the Earth so well, and then we have radio waves. So from the surface of the Earth, we can look out into space with the visible light, we see stars with our eyes, and with radio waves. Okay. Now, we have to think about light in two different ways, right? So I've talked about light as a wave, and we even use the word waves. But when we actually detect light, whether it's with our eye or a camera, your CCD camera in your phone, or however that works, we're actually counting light particle by particle. And what exactly does that mean? And that's important for what we're going to think about. When we measure light in radio waves, indeed, we actually use it as a wave, usually.
And one of the key elements of light is it behaves like everything, in fact, behaves both as a wave and a particle. And we'll do an experiment, I think. Maybe you'll get this to work. It works for me, but it might not. It works for some people are able to do this, but we'll see whether you can, will make it work for you, where we demonstrate that light is a wave. But basically, the first thing one has to do is say, well, what's the difference between particles and waves, and what do we expect to happen? So, for example, a particle it's localized in space. It's either here or it's there, right? It's not in both places. Where a wave actually is in a lot of places all at once. If you're in one particular location at one particular moment in time, there's no way to perceive a wave. A wave is really the change in something over space and time. So wave is both here and there. It's not localizable. And in the same token, a particle, when it goes from one place to another, let's say I had a particle, I detected it here, and then I detected it there, it's going to take some path between one place and the other. if there's no force on it, it'll take a straight line, which was Newton's law. Whereas a wave, it turns out, it'll take every possible path. So when I speak, like if I were to speak to someone around the corner where I can't see, they would still hear me. The wave will go around the corner. Whereas if I were to throw a ball to someone around the corner, it would never get there because the particle takes a particular path, whereas the wave can go around. You can't have half a particle, whereas a wave, you can make it any sort of amplitude that you want. You can always make the wave smaller. And one neat thing about waves versus particles is if you have one particle and another particle, guess what? You only have two particles. But if I take two waves, depending on how I add them together, I can end up with no wave at all. I can end up with two waves, or I could even end up with something 4 times as large as the original wave, depending on how we add them together. So there's some subtleties. But here we're going to think about doing an experiment here in the room, and maybe we'll try it in some different ways depending on how well it works. So if we imagine particles, and there's a wall, and there's a little opening in the wall, a window or whatever, and if we were to shoot particles at the wall, whether you can imagine them being balls or bullets or whatever, they'll go through that little opening in the wall, and you could ask, where do they hit? And they'll hit on a line corresponding to where the opening was, right? So it just does a straight line. Now, for a wave, what do you think is going to happen? Will it just go straight to the wall? This is representing a wave. You can imagine a wave in water or whatever, wave of light. What happens when it goes through that hole? Does it keep going straight? From your experience, maybe. Or maybe, yes, a guess. Just in contrast with the other one. When it leaves that little opening, it goes in all directions. Right? So if you imagine you have the ocean and an area that's protected, but there's a little opening for the boats to come through, for example, the waves on the ocean will generate waves through that opening, but it'll go in all directions once it passes through the opening. So there's a key difference. Now, but when we add, it gets more complicated where if we imagine we had 2 openings. And if we had 2 openings, well, in this case, we just get 2 stripes. That kind of makes sense. But if we have 2 openings with a wave, it's going to be a little bit more complicated than our previous picture, because the first opening acts like a source for waves going in a circle, and so does the second opening. So there'll be places where the peak from one opening will meet the peak from another opening, so the wave will be very big. And there'll be places where the peak from one opening will meet the trough from the other opening, so it'll be small. Oh, that doesn't look right, does it? That's weird. Sorry about that. It's just not rendering right on the screen. There should be stripes over here on the left. And I think they'll be on the right. I think there'll be stripes when you look at it on your computer at home. When you, I think you can see that. So the experiment we're going to do is imagine there's one wide slit. That's the best we can do with what we have in our hands. And when it goes to a wide slit, if it's a particle, you would expect it to be equally bright through the slit. And if it's a wave, well, you would get some interference. And you can see I've kind of drawn that heuristically. And the question is, well, can we try to do this? And let's see if we can get the lights to work in a nice way. So we have podium left, podium right, all off. I'm going to make it dark in here. We can do it in different, why is it not going? Off, and those guys. So how many of you can see those bright lights above me? Can you see them directly, any of you? No, they don't work. So we'll do it differently. I can do it, but you can't do it. All on. Okay, so what I'd like you to do is, if you look at these lights above you on the fluorescent lights, what I want you to do is to take your fingers and try to squeeze the light in between your fingertips. So between your thumb and your index finger. And as you squeeze it, at least just before they touch, what I see, and maybe you see, is in between your fingertips, you'll see that it doesn't turn off all the way. What you'll see is a whole bunch of, maybe, depending on your eyesight, one black line or several black lines that appear between your fingertips. As you're trying to squeeze the light in between your fingertips, what you'll see is before they touch, and you'll feel them touching, before they even touch, you'll notice it'll get dark in between your fingertips, and you'll also notice that it's not uniformly dark. It'll be dark and light, more or less light will squeeze through there. So what's happening there is that we're squeezing light in between. So these two black things are your thumb and your index finger, and your eye's over here, and what you're perceiving in your eye as bright light and dark is the interference of the waves of the light that comes very close to one fingertip and very close to the other fingertip. Now, it happens when it's here, too, when they're far apart, but it's much more subtle. It becomes important when you're squeezing light in a small region. So like, if you imagine your fingertips are about 1 millimeter apart. Your fingertips are 1 millimeter apart. And those stripes that you're seeing with your eye, I suspect, are barely, it's very hard for you to focus on those little stripes, but they're there, right? But you see them. Those stripes, the other number that you're thinking about is, if I could barely see them, if you remember, I talked a little bit about what you can perceive with your eye is about something like a 1/60th of a degree, loosely, right? So what you're seeing in your eye are stripes that are 1/60th of a degree apart. So I can take those two numbers together, believe it or not, and we have 1 millimeter is the width of the slit, and the angle of the fringes, we'll call it, whoops, wrong way, times the angle of the fringes is something like the wavelength of the light. So if we were to think about multiplying these together, those angle of the fringes is 1 part per thousand. And you multiply it by a millimeter, you'll get something like 1/1000th of a meter, which is the wavelength of the light that's squeezing through your fingers. So that's why if I were to make it, let's say I were to make the space between my fingers 1 centimeter, the fringes would be 10 times smaller, and you wouldn't perceive them. They'd be less than you can perceive with your eye. Instead of having 2 or 3 fringes in between there, there'd be hundreds. You just won't notice it getting brighter and fainter. It'll be very subtle. So the point is, like, if we were to make the squeezing even smaller than a millimeter, the fringes will appear bigger. But we have that combination. So if light were really a particle, it would either be on or off. But when you squeeze, it's like weird. It's like half on, half off, and on here and off there. So people realized this early on when they were studying light in detail, that it behaved like a wave. So light is a wave. And a wave has different properties about it, and we've talked about some of them. Just here, we have the wavelength of the wave. So that's the length over which the wave repeats, which we give the symbol lambda for length. We have the period of the wave, which means if I'm standing in one place, how often does it repeat? That's the period. Or that's the time over which it repeats is the period. The frequency is how often it repeats. So if it repeats once per second, that's a frequency, and we call that 1 hertz. Hertz means once per second. So for example, when your telephone, your cell phone, is about 2.5 gigahertz, 2.5 oscillations, 2.5 billion oscillations per second. That's also similar to the frequency in the microwave oven, is about 2 gigahertz. That's radio waves, okay? The radio waves that you listen on the FM radio is about 100 megahertz, 100 million oscillations per second, okay? Now, if we combine the wavelength and the frequency, that will give you the speed of the wave. So, I was telling you that you could measure the wavelength of the radiation in your microwave oven if you wanted to. And if you measure the wavelength of the radiation in your microwave oven, and you look on the door, inside the door, it will tell you the frequency of the microwave oven. In fact, it's like 2,450 megahertz usually. If you multiply those two numbers, you'll measure the speed of the wave in the microwave oven, which is the speed of light. Right? So you can use your microwave to measure the speed of light. If you want to do it, it's tasty. So different ways of doing it. If you want to do it, you have to remove the thing that makes the microwave oven rotate, not the oven itself, but the tray. And then put a plate in there, maybe a paper plate. And if you want, for me, the best thing is like thinly sliced cheese. And put that in the microwave oven for whatever, 15 seconds. And what you'll notice is that the cheese melts not uniformly. That's why the oven rotates, right? Why the tray rotates. You'll get stripes. And those stripes are the space between, it's not a whole wavelength, but where the wave is going up and down a lot, it goes up and down a lot here, and it goes up and down a lot there. So that's half a wavelength. So try it if you want to. If you don't like melted cheese, you can put chocolate chips on it and look for where the melted chocolate chips are. Measure that distance, and that will give you half of the wavelength of the microwaves in the oven, and multiply that by the frequency on the oven times 2. That should get you the speed of light, if you want to do that at home. There's other fun things to do with a microwave that maybe we'll do later when we do the sun, which is next week. I might bring my microwave oven down here and show you something cool. So we have light being a wave. You can see it's a wave when you squeeze it in your with your finger. If you look at your microwave oven, you'll see the effect of it being a wave in these stripes that you do when you heat up the cheese. If it were a particle, all the cheese would get hot. Why would the particles be here or there more often? They just bounce around the box. But light doesn't work like that. But on the other hand, light also behaves like a particle. And this was the big puzzle that led to this quantum mechanics, that everything is both a wave and a particle, it turns out. So around the turn of the 20th century, physicists discovered something weird. Like, if you had a metal, it could be whatever metal you like, and you could shine light on it, and that light shining on the metal would allow a current to flow. It causes a current to flow. So, okay? But then what the puzzle was is, if you make the light brighter, the current gets bigger. Okay, that makes sense. I make the light brighter, the current gets bigger. More light, more current. But if the light were too red, well, no current would flow at all. there was like a threshold in color that determined whether a current would flow at all. So why is that a puzzle? And this threshold of color depended on the type of metal. So light is always delivering energy. So if light is a wave, imagine light is a wave. Sure, if I make it red light, the wavelength of the light is larger, but I can turn up the intensity and deliver the same amount of energy to the metal. So surely a current should flow, but it doesn't. And this color depended on the type of metal. So Einstein, the same Einstein of everything else, came up with a solution, which was people knew at this time that current was carried by particles called electrons. So electricity was carried by individual particles called electrons. And people knew what the charge and the mass of one of these single electrons was at that time. So what Einstein figured, maybe quite naturally, was that the electron is trapped in the metal, and I have to give the electron a certain amount of energy for it to escape from the metal and a current to flow. Okay? But then the second ingredient, the important ingredient, which was a little bit of a jump, was that, the light itself is divided into particles, and the energy of each particle was proportional to its frequency. And that constant of proportionality we call the Planck constant, for a reason that'll become apparent like in a couple minutes. So what would happen is let's say I'm trying to excite the electron out of this metal. The electron really wants to take energy one at a time, right? So the photon comes in. If it's a red photon, the electron goes, that's not enough to get me moving. And it just ignores that red photon. Red photon kind of penetrates into the metal and is absorbed, but not by an electron that's going to leave. A blue photon comes along. It has enough energy for the electron to escape. The electron absorbs it and escapes. Now, if you give the electron lots of red photons, it doesn't accept any of them. It doesn't matter how many red photons, that each one doesn't have enough energy to make the electron to do anything, so the electron does nothing. You give it one blue photon, bam, it's out. And that's the basic idea. So the light has to come in little packages, and they're very small packages. But in fact, when you squeeze the light between your fingers like that, there's really only one of those photons in your finger, between your fingertips at any one time. So it's a small package, but it's not, we can measure it packet by packet nowadays. So like when you take a picture with your camera phone, right, a phone in your camera, each pixel in the picture, they've changed the numbers to make it pretty for you to perceive, but basically the number that your phone measures is how many photons hit that pixel in the camera. Your camera is counting photons. They're small and their energy is not very big, but it's entirely within the realm of technology you hold in your hands to count them one by one. In fact, your eye basically counts them one by one as well. Okay. So this is called the photoelectric effect, and we use it all the time, right? So there was a second puzzle, and I'll show you what this is, which had to do with the idea of black body emission. So what is black body emission? Black body emission is basically how things glow when they get hot. Things that are dull, like these nails, they don't have a particular color to them. I know they're a bit shiny, but they're kind of dull. It's not like your red shirt is red not because it's glowing with heat, so this is the emission you get from something when it gets hot. And a good example of a black body is, the definition is, if a bit of light hits a black body, it's very, very likely to get absorbed. That's the idea. So a black sweater would be like a black body. Or your oven. If you have an oven, you look in the oven, it's dark in there, right? Light doesn't bounce out of your oven very easily, especially if your oven had a tiny little window, right? You wouldn't be able to, so the emission inside your oven when it heats up is what we call black body emission, right? So people in the late 1800s were measuring the properties and thinking about this black body emission. And I'll show you what it looks like with this device. And as I heat up the nail hotter and hotter, and I'll turn it all the way up to 11, it will get brighter and brighter, as you're noticing, but also, I'm supposed to sort of record it. It's going to start sparking. That's kind of exciting. And then I let it fall apart, so there's no power flowing through there. But you can see as it cools, it gets fainter. It gets more and more red, right? And this nail essentially emits radiation like a black body. And as it gets cooler and cooler, you can see it's getting fainter and fainter and redder. Eventually, we won't perceive it glowing. Perhaps your digital camera with your phone, for example, is sensitive to a bit of infrared radiation, so it might even be bright in your camera, even though now we don't see it as bright as all. I destroyed the nail. Everyone likes you to glue it back together in the end, so I'm going to glue it back together, or try to. You kind of have to weld it, right? And then shut it off. I think that'll be fine. So what you've seen there with that nail glowing, there are a couple of facts, right, that maybe you noticed. First of all is that it gets, as it's hot, when it's hotter, it's brighter. Fact one. Fact two, when it's hotter, it goes from being red to yellow, or red to orange to yellow, and so on. Those are the two things. A third thing that you might have been able to measure if you had a more sensitive or a different instrument than your eye is that the spectrum is continuous. And we'll talk about spectral lines, but the spectrum is continuous. So this seemed like a rather simple thing, and people did this experiment, and you could see what happened there, and it sort of made sense with people were familiar with what was going on. So the physicists realized that if you had an object which really absorbs almost all the light that hits it, its spectrum of radiation would only depend on the temperature. So as we were heating this up, the temperature of that thing was getting higher and higher, and the spectrum peaked further blueward as we went along. So they realized that, and they calculated what would the spectrum look like. And they didn't get that it would be brighter or fainter. They realized it would be brighter and fainter depending on the temperature. But when they calculated how much energy would be coming out of this glowing nail, it was infinite. So clearly they had made an error in one of their assumptions, right? None of us, like I turned this on, none of you are harmed. If there were an infinite amount of energy coming out of that nail, we'd all be, in trouble now. It would be bad. And clearly, the physicists there was some mistake that they made. So, we didn't see that. No one died right now. It's not what we actually observed. And Planck why it's called H, is called the Planck constant, he realized if light came in these little packages, this is before Einstein's point, you could make it work, right? That if light doesn't come like a wave, I could have a really, 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 really small amount of light at a given frequency. But what Planck said is no, you can't have a tiny, 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 once it carries an energy equal to h times the frequency, you couldn't have it be any less energy. And in fact, you could only have light in multiples of that energy. It came in little packets. And by calculating what happens if it comes in these little packets, they were able to explain the spectrum that you saw from this nail or from the inside of the oven, something that everyone knew what it was like. People at that time had been looking at hot pieces of metal for hundreds of years. I mean, that's how people would work glass or metal. You would know when it got to this color, you could hammer it. Or if it was glass and it glows in that color, then you can start working it. And people knew that the peak of what the color of the metal looked like reflected the temperature of that object. And so here's what the spectrum looks like. So when it's around 5,000 degrees, not coincidentally, when it's around 5,700 degrees, to be more precise, the spectrum peaks at the maximum level of our vision. So why would that be? Why do you think? Why would the spectrum peak right in the visible around 5,000 degrees? Can you think of anything that's 5,000 degrees? What? The sun. The sun is 5,700 degrees. So our eyes are evolved to be most sensitive where the sun puts out most of its radiation. Not a coincidence, right? Now, our little nail did not get that hot. So our nail might have been 3,000, 4,000 degrees at the best, right? And so that's why, these lights, like in the front here, are lights which you can't see so well. These spotlights have a glowing piece of metal in them. And that glowing piece of metal might get to be up to maybe 4,000 degrees. So the light from the spotlights is a little bit redder than sunlight, okay? Because we can't get the inside of that thing to be as hot as the sun, I'm afraid, the piece of metal. So our little iron nail was peaking when we got it sort of warm, 3,000 Kelvin. If you look at the spectrum, it goes up in the red, so the red it looks red. Here, this ratio between red and yellow isn't so dramatic, so it looks orange, because it's a mixture of red and yellow and not much blue and so on. And if we get up to here, around 5,000 or 6,000 degrees, it's what we would perceive as white, because that's the color of the sun, right? It's white. That's sort of the definition of white, almost. Now, so this shows what was actually observed, and then this is when people tried to calculate it. It just kept going up and up and up and up. So everything would look really, really blue-white, but it doesn't, right? So the thing we noticed with our nail is as the nail got hotter, it got brighter. And when you think about what these black bodies do, the power that comes out of the black body is some constant, which you don't really need to know, times the temperature to the fourth power. So when I double the temperature, when I go from 2,000 to 4,000 degrees, that nail got 16 times brighter. Okay? The last term is the area, the surface area of the nail. If I were to put two nails in, it would be twice as bright. That's basically what that term is. But the big factor is the temperature. I double the temperature, the power goes up by 16, and that's important. Okay. And the second idea that we can see from the curve, but also from the experiment, is as the black body gets hotter, the peak gets bluer. Hotter black bodies peak at bluer temperatures. And in fact, the wavelength of the peak times the temperature is a constant. So, if I go out and measure the radiation from a star, and it turns out stars, imagine if you shine light into a star, it doesn't get out. It gets absorbed by the star. Stars, to a good approximation, emit like a black body. There's differences, of course. But if I measure the color of a star, that can tell me the temperature of the star. I don't have to go there with a thermometer. I can look at the radiation coming from the star and measure the temperature. So this is just showing where the peak lies in wavelength as a function of temperature. And you can see it's moving towards the right, and then also or moving towards the left, and the height goes up dramatically as we increase the temperature of that black body. So you can see at 6,000 degrees, the peak is somewhere between yellow and green. And 6,000 Kelvin is a little bit hotter than the sun. But notice how much dramatically higher 6,000 is than 5,000. That's that temperature to the high power playing a role. All right. So here is what the sun looks like. This is the spectrum of the sun, and we have some different curves here. So the yellow region is what the sun looks like above the atmosphere. So the atmosphere, if you notice, at the ultraviolet end over here, it goes from here down to here, and that's due to the role of ozone. So that's why we worry about if there's a lack of ozone, the more ultraviolet radiation passes through the atmosphere. So that's this deficit. If we look in the infrared, you can see water absorbs infrared radiation, also carbon dioxide. And the reason that's why water and carbon dioxide act as what we call greenhouse gases. They absorb infrared radiation. So basically what's happening on Earth is the sunlight comes, it's absorbed by our atmosphere, boom, it reaches the surface of the Earth heats up, it re-emits infrared radiation because the surface of the Earth is not almost 6,000 degrees, and that infrared radiation gets absorbed by the atmosphere here and here and here. But the key thing to keep in mind is what's plotted here is a black body spectrum. It's written in degrees Celsius, so you have to add 273 degrees on it to get degrees Kelvin, which we're normally going to use. So that's around 5,523 degrees Kelvin is the spectrum. And you can see that spectrum is approximately what the sun is doing, that yellow curve. So real stars emit like black body. There's some colors, there's extra light. It's not perfectly smooth, right? It's jubbly here. And at some colors, there's too little light, right? There's dense. And to talk about what those dents are and the excesses of light, we'll talk a little bit about how we make different sorts of spectra. So this continuous spectrum, from my nail or you can get it from a liquid or even a gas, occurs when the gas is so thick or the material is so thick that it's opaque. You can't see through it. And that gives you a continuous spectrum. Now, an absorption spectrum, what's happening there is if we have the gas the material that's glowing, that's incandescent, the continuous spectrum, and in front of it, we have some gas that's cooler, but not very dense, so we can see through it. That cool gas is going to absorb some of this radiation coming from the star or whatever's emitting the light, but it's only going to absorb where it feels like it. There are certain energies, depending on the property, the material, that it will absorb the gas. The gas will absorb the light much more easily. And these particular places, they're called absorption lines. And they depend on what the material is made out of. Now, on the other hand, if we imagine that same gas, that same material, it's not opaque. We can see through it. It's tenuous. But I heat it up, so the atoms are excited nevertheless. Those atoms will emit radiation in lines that correspond to exactly where it was absorbing, the exact same colors. And that's the Loder spectrum is called an emission spectrum. Now, in astronomy, essentially everything we see is one of these three types of spectra. You can see it. So here's just a picture showing how it would work. If I have a star, and let's say I look directly at the star, I would see a continuous spectrum. But let's imagine that there's a cloud of gas between me and the star, and it's going to absorb some of this radiation. So I'm looking through the gas from over here. What I'll see is this continuous spectrum, the same as was over here, but with absorption lines. Okay? That makes sense, I hope. Now, if I were to look at that same bunch of gas, but from the side, that gas is being excited by the starlight, but we don't see the starlight. We just see the evidence of them being excited, those atoms, so we see emission lines. So basically what's happening is the light starts at the star, the gas pulls out some fraction of the light in these lines, and then emits it in all directions. So some of it does get emitted in this direction, but only a small fraction ends up being sent back in exactly the same way it came. So we see a dark line over here, but if I look at any other direction, I'll see those emission lines. And those emission lines tell us what is in that gas. So people realized that different sets of materials had different sets of lines, and that the emission lines are the same colors as the absorption lines for the same material. So they concluded, well, materials like to absorb and emit radiation at specific colors. Now, if we think about what we learned from Planck, a given color is a given energy. Remember when we talked about the metal, I needed enough energy for the electron to leave the metal. Now, if you think of atoms, I need certain amounts of energy to make electrons move around in atoms. And those energies are given by these spectral lines. So in hydrogen, it has a relatively simple spectrum. We have a red line, and then a greenish line, a blue and purple. And then let's think about helium. It's not so complicated. Sodium is weird. It has a simple spectrum too. And we use that in lights. But neon, look, neon's wacky, right? There's lots of lines there. Can anyone guess why something like hydrogen has a simple spectrum? Well, imagine how, yes?
It has fewer electrons.
It has just one electron. So, one electron has not that many ways to move compared to neon, which has 10 electrons. Those 10 electrons can do all sorts of different things, and so you have lots of colors. Now, sodium is kind of simple because sodium is in that first column of the table. where there's one electron that's more loosely bound than the rest. So it's that one outermost electron, similar to hydrogen, that is interacting with the light. So the atoms in that first column also have relatively simple spectra. But where the colors are is unique to each atom. So one can look at the sun, and that's what they did. And when they first looked at the sun, they found this yellow line, which isn't the exact same place as where sodium is. There was no element who had that yellow line that had been discovered so far. So Norman called it helium because it was from the sun. I wonder if we have a spectrum of the sun. I'm going to skip ahead. Maybe I don't. I'm going too fast. Okay. So if you look at the sun, you see tons and tons of spectral lines, and we'll talk more about that next time on Monday when we start talking about the sun. But the first thing they noticed was that the sun apparently had an element that didn't exist on Earth. And one thing one had to start thinking about is, how do the materials decide what energies of photons that they're going to absorb, or better yet, where do the electrons live in these atoms? We wanted to understand them. So there was this first idea of how an atom works. It was called the plum pudding model. And the idea was that the atoms or materials was like a plum pudding, which means that there was plums, which was the positive charge, that were interspersed everywhere, and the negative charge, the electrons, which we knew were already at this time, were lighter and they could move faster. They were uniformly distributed throughout, right? So Rutherford decided to do an experiment where what he did was he shot charged particles, actually helium nuclei, at a piece of gold foil. Now, what you would expect on the left is what he expected. So as stuff went through the gold foil, most of the particles would more or less pass through, and since the positive charge wasn't concentrated anywhere in particular, you would get things going a slightly different direction, but nothing very dramatic. But what he found was over here on the right-hand side, that occasionally this particle would go into the gold foil and it would literally bounce back again. It would bounce right back. So it would come along from here, and most of the time it would kind of go straight through, but occasionally it would just go bam, straight back, like in this picture. So what he concluded was that in an atom, all of the positive charge and all of the mass, in fact, was concentrated in a very small region whose radius was maybe 1/1000th of the radius of the atom. And the rest of the atom was where the electrons lived, and it was essentially devoid. There's electrons, but they have very little mass. They have and they have charge, and they're just flying around. And this idea allowed people to now first try to understand what atoms were like, because we knew what the structure was.
So where we ended up was this experiment of Rutherford, where he shot helium nuclei at a piece of gold and found that they would bounce back occasionally. So this very, at the time, thought to be very heavy object, the helium nucleus, you could figure out an idea of what its mass was, and it was about 8,000 times the mass of an electron. So it's a heavy thing, this thing that they were shooting at the gold, and occasionally it just came right back. So think it's a factor of 8,000. So this was the metaphor he used. It was as if you fired a 15-inch shell at a piece of tissue paper and expected it to just pass through, and then it ricocheted back at you. There was no expectation that there'd be something so dense within the gold foil. And they came to the conclusion of what the nucleus looked like. So what they realized is that the positive charge was concentrated in a very dense ball called the nucleus, and the negative charge was surrounding the nucleus. And this was a lovely picture, especially from the astronomy point of view, because it's reminiscent of our solar system. So people immediately had these ideas that, well, the positive charge would attract the negative charge, and these negative charges would orbit the nucleus just like the planets orbit the sun. The force law is exactly the same, 1 over r squared. Okay? So when they did this, they immediately came to the realization, well, this electron is going around the nucleus, and when you move electric charge around, it emits radiation. They had radios and stuff. They knew about that. So as this electron's orbiting the nucleus, it would normally emit radiation, and then eventually the electron would spiral all the way into the nucleus, and then you'd be done, and there'd be no atom. And that would take a very short time. So they said, well, maybe the electron is only allowed to have certain orbits around the nucleus. And the first guess that they made was that, well, if the electrons are waves, right, not just particles, but they're waves, they can act both ways, you would imagine that an electron, as it goes around, would have to have a given number of wavelengths in that circle. And that model actually worked quite well for hydrogen, this really basic idea. So what you would do is the electron could exist in different orbits, which I've drawn with these circles, and it could only be there. It couldn't be anywhere else. And there would be an innermost orbit, and beyond that it couldn't get any closer to the nucleus, okay? So they're forced to travel in specific levels around the nucleus, and that's the key big result of quantum mechanics, was that you could explain all these elements now and their chemistry and why different elements act in different ways comes down to these electrons being waves around the nucleus. But in particular, what it meant is electrons could jump. They could drop from one level to another. And since these levels are discrete, like steps of a ladder, the electron can't live anywhere in between these levels. So when it would drop down to a lower level, it would lose some energy. It would emit that energy in a photon. Here I've done a blue photon. But since the levels were in certain spots, those energies would always be the same for a given atom, because the rungs of the ladder are determined by what type of atom you are. So here it absorbs a photon, the red photon comes in, and it jumps up to a higher level. And when it drops back, the photon gets emitted, and it's the exact same energy as the one it just absorbed. So this idea of the electron sitting in levels around the nucleus accounted for those spectral lines. And depending on the atom, different atoms had different sets of levels. So for example, if you have a bunch of complications, right? So we think about hydrogen, that's the simplest. It's one electron and one proton. And we can calculate all those levels very easily without a computer, and they're spot on. Now if we go to the next most complicated atom, helium, it has 2 electrons and a nucleus. And those electrons interact with each other. There's 3 objects now. Nucleus, 2 electrons. 3 is so much more complicated than 2. And helium, we can't calculate it without a computer. But we can, with a computer, we can go through all of these and calculate in detail where all the levels are going to be, compare it with what's observed. So we understand that periodic table in terms of the electrons living in different levels. So each atom has its own set of spectral lines that it's going to emit. But we'll talk more about this later, but you probably literally heard the Doppler effect. But if a source of radiation is moving towards you, the wavelength of the radiation that you will observe will be slightly shorter than the one that's emitted. So when, for example, if an ambulance is coming towards you, you'll hear it at a higher pitch than when it's moving away from you. That's you hearing the Doppler effect in your ear. The police radar gun works with the same thing. The radar bounces off the car, comes back, and you measure the frequency going out and the frequency received, and if that difference is too large, guess what? You're speeding. It's that simple. So here we imagine that the star, each atom in the star is absorbing photons of a given energy, but if the star is rotating, some of those atoms, the ones on the left, are moving towards us. So when they absorb, their radiation that they're absorbing is blue. And on the other side, it's moving away from us. So it's a little bit red of the ones who are not moving towards or away. So when we look at the star, we can measure whether it's rotating or not, for example. We can measure how fast the star is moving away from us or towards us, because that spectral line that we see, that we observe from the star, we can compare to one that we have in the laboratory where it's not moving towards or away from us. It'll be shifted by a little bit. If it's moving away from us, it'll be shifted to the red. If it's moving towards us, it'll be shifted to the blue. So some stars rotate really fast. So, for example, the sun rotates about once a month. That's a coincidence. The moon goes around the Earth once a month. The sun goes around its axis once a month. Altair is a star, it's in the constellation the Eagle, which is right next to the Swan, if you've seen the Swan in the sky. Altair is a star. It rotates every 6 hours, right? Not 20 days. It's a more massive star than the sun, and it's noticeably squished. It's rotating so fast. And if we measure the spectral lines from that star, we can determine how fast it's rotating. For the sun, it's really small, right? The sun's big, but it goes around 30 days, and its radius is 600,000 kilometers or something. And in 30 days, 600,000 kilometers, it's a long way to go, but it's still not. It's only a couple kilometers per second. So another neat thing that you can see is if two stars are going around each other, right, what you'll find is one star is going towards us sometimes, and sometimes it's coming away from us. And sometimes you can see both the stars. So on, let's see what these different pictures are. So here we have, in figure 1, both of the stars, one's moving towards us, one's moving away from us. We see a spectral line. It's shifted a little bit towards the yellow for the one who's moving away from us, a little bit towards the green for the one who's moving towards us. A little bit later in the orbit, they're both moving in the plane of the sky, so we get the wavelength of the line at rest, more or less, in the middle, and then it repeats itself. Now star A is moving away from us in number 3. Now, we can even, the two stars, they have tons of spectral lines, right? And they're all doing this. And from one star, the spectral lines could have different ratios. One star could be hotter than the other. One star could have more of this and that than the other. So we can actually tell which star is which as they're going round and round, these spectral lines. And that lets us figure out what is the mass of each of these stars, for example, because it's the same exercise we did for the Earth going around the sun. We'll know how long it takes to orbit and how fast it's moving in the orbit, and that's how we figured out the mass of the sun, if you remember. How long it took, or how big the orbit was, and how fast it is to go around. And we can measure this for stars that are in pairs as well. So, the location of the spectral lines and the width can depend on how the individual atoms are moving. If the gas is hotter, they're moving faster, and we call that thermal broadening because it has to do with heat. If the star has a magnetic field on it, that will affect how the electrons go around these atoms in their orbits, believe it or not, and that will change the location of those spectral lines. The star can rotate, we talked about that. The stars can be moving, so we can have binary stars or the star moving towards or away from us. One thing that's kind of maybe a little bit counterintuitive is if the gas is a high pressure, not necessarily high temperature, the lines will also be broadened. And that's kind of weird, but it has to do with how quantum mechanics works. So a star, two stars at the same temperature, where one is the gas is very dense and one where the gas is very diffuse, the one with the diffuse gas, the spectral lines will be very much narrower than the one where the gas is dense. So we can measure all of these things from the spectrum of the star. So we can figure out the temperature from the color of the star, how fast the star is moving by the Doppler effect, the magnetic field of the star because of the Zeeman splitting, so that affects the location of all the spectral lines. And with all this information, we can infer the age of the star, we can infer sometimes how bright it is inherently.